You've been lied to. The speed of light is useless. Everything you've seen in movies, every sci-fi story you've loved, it's all built on a beautiful, devastating lie. Because even if you could travel at light speed, you'd still be pathetically slow. If you're curious about these mysteries, make sure to subscribe to this channel and give a thumbs up. Now let's begin this journey. Today, we know this speed limit is absolute. Nothing with mass can ever reach the speed of light because it would require infinite energy. But let's set that inconvenient fact aside for a moment and imagine we somehow built a spacecraft that could travel at light speed. Maybe we discovered some revolutionary propulsion system. Maybe we found a loophole in physics. Maybe we just decided to ignore reality for the sake of argument. Either way, we're now piloting a photon-fast starship ready to explore the universe. Where should we go first? Let's start with our cosmic backyard, our own solar system. Here, traveling at light speed actually feels pretty good. You could zip from Earth to the Moon in just 1.3 seconds. The Moon sits about 238,855 kilometers away, and at light speed, that's practically nothing. You'd arrive before you finished reading this sentence. Traveling to Mars would take you between 3 and 22 minutes depending on where both planets are in their orbits. When Mars is closest to Earth, about 34 million kilometers away, you'd get there in 3 minutes. When it's on the opposite side of the Sun, about 250 million kilometers away, the trip takes about 22 minutes, still manageable. You could have a conversation with colonists on Mars with less delay than some video calls experience here on Earth. Venture out to Jupiter and you're looking at about 35 to 52 minutes depending on orbital positions. An hour doesn't sound so bad for visiting the largest planet in our solar system, does it? Saturn, with its magnificent rings, sits between about 66 and 96 light minutes away, so roughly an hour to an hour and a half. You could watch a movie during the trip. Neptune, the most distant official planet in our solar system, would take you about 4 hours when it's at its closest. Even reaching the edge of our solar system, let's say the heliopause where the Sun's influence finally gives way to interstellar space, would only take you about 17 hours at light speed. The Voyager 1 probe, humanity's most distant ambassador, crossed this boundary after traveling for more than 35 years. At light speed, you'd catch up to it before a full day passed. Within our solar system, light speed feels powerful. It feels like a legitimate way to travel the cosmos. You could explore every planet, visit countless moons, investigate asteroid belts, and study comets, all within time frames that feel comprehensible. Days, hours, minutes. These are intervals we understand. These are timescales we can wrap our minds around. But here's where everything changes. Here's where the universe reveals its true scale and reminds us just how small we really are. The moment we try to leave our solar system, the moment we attempt to visit even our closest stellar neighbors, light speed transforms from feeling impressively fast to feeling desperately inadequate. Consider this. Our nearest neighboring star system is Alpha Centauri, which is actually a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Proxima Centauri is the closest of the three, sitting at about 4.24 light-years away. Now, what does 4.24 light-years actually mean? It means that even traveling at light speed, at that ultimate cosmic velocity of 186,000 kilometers per second, it would still take you 4.24 years just to arrive at the nearest star. 4 years and almost 3 months of traveling at the fastest possible speed, and you'd only reach our closest neighbor. Think about that for a moment. 4 years of moving at a velocity so extreme that it would turn you into pure energy if it were actually possible. 4 years during which you'd cover about 25 trillion kilometers, and at the end of that journey you'd have visited exactly one star system out of the estimated 100 to 400 billion stars in our galaxy alone. But wait, it gets worse, much worse, because while Proxima Centauri might be our nearest neighbor, it's not exactly a cosmic hotspot. It's a red dwarf star, small and dim, And while it does have at least 3 confirmed planets, including one in the habitable zone, it's not the kind of destination that makes for exciting headlines. If you wanted to visit a star system more like our own, you'd need to travel considerably farther. Tau Ceti, a sun-like star that's been the subject of countless science fiction stories, sits 11.9 light-years away. 12 years of light-speed travel just to check out a star that kind of resembles our own. Epsilon Eridani, another relatively nearby sun-like star, is 10.5 light-years distant, 10.5 years to get there. Sirius, the brightest star in our night sky and actually a binary system, lies 8.6 light-years away, almost 9 years at light speed to reach the star that ancient Egyptians used to predict the annual flooding of the Nile, the star that has captivated human attention for millennia because it shines so brilliantly in our sky. 8.6 years to actually visit it. Now here's where I really want to drive this point home, because I think it's easy to hear these numbers and not fully grasp what they mean for actual space exploration. Let's talk about Voyager 1 for a moment, because it provides the perfect reality check. Voyager 1 was launched by NASA on September 5, 1977. For nearly 50 years, this incredible piece of human engineering has been traveling through space, leaving our solar system behind and venturing into the vast darkness between stars. As of November 26, 2025, Voyager 1 is traveling at approximately 11 kilometers per second. That sounds fast, right? 11 kilometers every single second. It's moving at about 38,000 kilometers per hour. No human-made object has ever traveled faster in terms of speed relative to the Sun. And yet, despite moving at this impressive velocity for almost half a century, despite covering more than 15 billion kilometers, Voyager 1 is still only about 0.024 light-years from Earth. It will be 1 light day away from us in November 2026. 1 light day, not 1 light year. 1 day's worth of light travel after almost 50 years of constant motion. Let me put that in perspective. At its current speed, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. 73,000 years. That's longer than all of recorded human history. That's longer than human civilization has existed. When Voyager 1 was launched, scientists included the famous Golden Record, a time capsule containing sounds and images from Earth, meant to communicate the story of our world to any intelligent life that might eventually find it. The people who created that record, the engineers who built Voyager, the scientists who calculated its trajectory, they're now in their 70s and 80s, if they're still alive. Meanwhile, their creation has barely begun its journey across the cosmic ocean, moving at what we consider an impressive speed, but what the universe considers an imperceptible crawl. And this is with our fastest spacecraft. This is the best we can do with current technology. We haven't even discussed the engineering challenges of building something that could actually approach light speed. We're just talking about the distances involved, assuming you somehow already have a light speed vessel. The takeaway here is sobering. Even at light speed, interstellar travel within our immediate cosmic neighborhood requires years or decades. And we're still just talking about nearby stars. We haven't even begun to explore the broader galaxy. We haven't discussed visiting the fascinating places where stars are being born, where black holes are devouring matter, where the most exotic phenomena in the universe are occurring. We're just talking about popping over to visit the stellar house next door, and even that takes years at the universe's ultimate speed limit. But as disappointing as this is, it's about to get so much worse, because when we zoom out from individual stars to the scale of our entire galaxy, that's when light speed truly reveals itself to be hopelessly inadequate. That's when the universe shows us just how vast, how incomprehensibly enormous reality truly is. Let's talk about our galaxy, the Milky Way. This is our cosmic home, the vast spiral of stars, gas, dust, and mystery that contains our solar system along with hundreds of billions of other star systems. When you look up at the night sky on a clear, dark night, away from city lights, that misty band of light stretching across the heavens is actually you looking into the dense disk of our own galaxy from the inside. It's a humbling view, a reminder that we're embedded within something almost incomprehensibly vast. But just how vast are we talking? The Milky Way is enormous. According to the latest measurements from studies published in 2024 in Nature Astronomy, our galaxy has a diameter of approximately 100,000 light-years from edge to edge. Some measurements suggest it might be even larger, but let's work with that conservative estimate of 100,000 light-years across. Now remember what we just established about light speed. Remember how it takes over 4 years just to reach our nearest neighboring star. Remember how Voyager 1, after nearly 50 years of travel, has covered only about 0.024 light-years. Now imagine trying to cross the entire width of our galaxy. At light speed, traveling from one edge of the Milky Way to the other would take you 100,000 years. 100,000 years of moving at 186,000 kilometers per second. 100,000 years during which you'd cover approximately 587,000 trillion kilometers. To put that in perspective, when humans first left Africa and began spreading across the globe, roughly 70,000 to 100,000 years ago, our galaxy was about the same size it is now. If some ancient human had somehow launched a light-speed vessel at that exact moment, it would just now be reaching the opposite edge of our galaxy. Think about everything that's happened in that time. The rise and fall of countless civilizations, the invention of agriculture, writing, mathematics, science, technology. The entire span of recorded history would fit into that journey multiple times over with room to spare. And that's just crossing the galaxy once. Just going from one side to the other in a straight line. But here's the thing, nobody explores a galaxy by simply crossing it in a straight line. If you actually wanted to explore the Milky Way, if you wanted to visit interesting destinations and see the cosmic wonders our galaxy contains, you'd need to make stops. Lots of stops. Let's say you wanted to visit the galactic center, the supermassive black hole called Sagittarius A star that anchors our entire galaxy. This monster black hole, which weighs about 4 million times as much as our Sun, sits approximately 26,000 light-years from Earth. At light speed, that's a 26,000-year journey just to reach the center of your own galaxy. You'd arrive having missed the entire span of recorded human civilization back on Earth. When you left, humans were just beginning to develop agriculture in the Fertile Crescent. When you arrived, we'd have built and destroyed countless empires, gone from stone tools to quantum computers, from cave paintings to the James Webb Space Telescope. Everything we consider history would have happened while you were in transit. Or maybe you'd want to visit the Orion Nebula, one of the most spectacular star-forming regions visible from Earth. It's a stellar nursery where new stars are being born right now, a place where you could witness the processes that created our own Sun billions of years ago. The Orion Nebula sits about 1,340 light-years away. That's 1,340 years of light-speed travel. When you launched your journey, Charlemagne would have just been crowned Emperor of the Romans. The Viking Age would be underway. Islam would be barely a few centuries old. By the time you arrived at Orion, the entire medieval period, the Renaissance, the Age of Exploration, the Industrial Revolution, the World Wars, the Space Age, everything that followed would all be ancient history. Perhaps you'd want to investigate the Carina Nebula, another stellar nursery but even more active and spectacular, home to some of the most massive stars known. It's located about 7,500 light-years away, 7.5 millennia at light speed. You'd leave during the Bronze Age and arrive in whatever world exists 75 centuries from now. The Crab Nebula, the expanding remains of a supernova that exploded in the year 1054, as witnessed by Chinese astronomers, lies about 6,500 light-years distant, 6,500 years to reach the remnant of a stellar explosion that people on Earth watched happen almost exactly 1,000 years ago. These aren't galaxy-spanning distances. These aren't trips from one edge of the Milky Way to the other. These are journeys to notable landmarks within our own corner of the galaxy, and they all require thousands of years, even at light speed. The sheer scale makes any notion of casual interstellar travel seem absurd. You couldn't have a galactic civilization where different star systems regularly communicate and interact. You couldn't have an empire spanning multiple sectors of the galaxy. You couldn't even have a coherent society spread across a few hundred light years, because any message, any signal, any communication would take centuries or millennia to arrive. By the time a distress call reached you, whatever civilization sent it would have long since solved their problem, or collapsed, or evolved into something completely different. Actually, if you want to get a visceral sense of just how slow light speed really is when dealing with galactic distances, I made another video that breaks down exactly how long it would take us to travel just 1 light year using our current technology. It's called How Long Would It Take Us to Travel 1 Light Year Nowadays? And I think it'll give you an even deeper appreciation for the mind-bending scales we're discussing here. Check it out after this video, because the numbers are genuinely shocking. The link is in the description and pinned on the comments. But let's get back to our main point, because believe it or not, we haven't even scratched the surface of how inadequate light speed is for cosmic exploration. Everything we've discussed so far, all these impossibly long journey times, have been limited to just our galaxy, just the Milky Way. We haven't even begun to talk about traveling to other galaxies. And that's where things go from discouraging to absolutely devastating. The Andromeda Galaxy, also known as Messier 31 or M31, is the nearest major galaxy to our own. It's a spectacular spiral galaxy similar to the Milky Way, containing roughly 1 trillion stars compared to our estimated 100 to 400 billion. On a clear autumn night in the Northern Hemisphere, you can actually see Andromeda with your naked eye as a faint, fuzzy patch of light. Ancient Persian astronomer Abd al-Rahman al-Sufi described it in the year 964 as a small cloud, making it one of the most distant objects visible to the unaided human eye. When you look at Andromeda, you're seeing light that left that galaxy 2.5 million years ago. You're looking back in time to an era when our ancestors were just beginning to use stone tools, when Homo habilis was giving way to Homo erectus, when our species as we know it today didn't even exist yet. That light has been traveling toward Earth at 186,000 kilometers per second for 2.5 million years just to reach your eyes. And here's the kicker. Andromeda is our closest major galactic neighbor. It's right next door in cosmic terms, and it's 2.5 million light-years away. Let's be absolutely clear about what this means. If you could somehow build a spacecraft capable of traveling at light speed, and if you pointed it toward Andromeda and launched today, you would arrive 2.5 million years from now, 2.5 million years. Humans as a species, Homo sapiens, have only existed for roughly 300,000 years. Recorded human history spans maybe 5,000 years. The entire story of human civilization, from the first cities in Mesopotamia to the smartphone in your pocket, covers less than 0.5% of the time it would take to reach Andromeda at light speed. You would need to make that journey 500 times over to equal the length of time we're discussing. Every person you ever knew, every culture that existed when you launched, every language, every nation, every ideology, every artistic movement, every scientific paradigm, all of it would be gone, not just changed, but completely vanished and replaced hundreds of times over. Species would evolve and go extinct, continents would drift into new configurations, ice ages would come and go. If Earth itself survived without human intervention, it would be a completely alien world by the time you reached Andromeda. And Andromeda is close. It's our neighbor. It's actually on a collision course with the Milky Way, moving toward us at roughly 250,000 kilometers per hour, or about 68 kilometers per second. In approximately 3.75 billion years, our two galaxies will collide and eventually merge. This sounds violent, but the distances between individual stars are so vast that very few actual stellar collisions will occur. Instead, the galaxies will pass through each other, their mutual gravity disrupting both structures, sending stars careening into new orbits, eventually settling into a new formation that astronomers have playfully nicknamed Milkomeda. But even this relatively nearby cosmic neighbor, even this galaxy that's literally heading toward us, is so far away that light speed can't bridge the distance in any reasonable time frame. Now you might be thinking, okay, but surely there are closer galaxies than Andromeda, right? And you'd be correct. There are several dwarf galaxies that orbit the Milky Way, satellite galaxies that are gravitationally bound to our own. The closest is the Canis Major Dwarf Galaxy, sitting about 25,000 light-years from Earth. But here's the thing, calling it a galaxy is almost generous. It contains maybe 1 billion stars, it's being torn apart by the Milky Way's tidal forces, and it's debatable whether it's a separate galaxy or just an overdense region of our own galactic disk. The Large Magellanic Cloud, visible in the southern hemisphere as a prominent patch in the night sky, is more substantial. It contains several billion stars and sits about 160,000 light-years away, 160,000 years at light speed. Still an incomprehensible journey for any civilization trying to make the trip. The small Magellanic Cloud, its companion, lies about 200,000 light-years distant. 200,000 years to reach a smaller, irregular galaxy containing several 100 million stars. Even these relatively nearby satellite galaxies require journey times that dwarf all of human existence. But let's push further. Let's look beyond our local group of galaxies, beyond our immediate cosmic neighborhood. The Triangulum Galaxy, also called Messier 33, is the third largest member of our local group of galaxies after Andromeda and the Milky Way. It contains roughly 40 billion stars and sits about 3 million light-years away, 3 million years at light speed. The Sombrero Galaxy, famous for its distinctive shape that makes it look like a Mexican hat when viewed edge-on, lies about 31 million light-years away. 31 million years to reach it, even moving at the universe's speed limit. The Whirlpool Galaxy, a spectacular face-on spiral that was one of the first galaxies where spiral structure was ever identified, sits about 23 million light-years distant. 23 million years of travel time at light speed. These galaxies aren't even particularly far away by cosmic standards. Astronomers consider them part of our relatively local universe. They're close enough that we can resolve individual stars in some of them using powerful telescopes. They're close enough that we can study their spiral arms, their star formation rates, their chemical compositions in considerable detail. And yet they're so distant that even light, moving at the fastest possible speed, takes millions of years to traverse the gap. By now you should be getting a sense of just how desperately inadequate light speed is for exploring the universe. Within our solar system it works fine. For reaching nearby stars it's painfully slow but theoretically manageable. For exploring our galaxy it becomes prohibitively time-consuming. And for traveling to other galaxies it's essentially useless for any civilization that operates on timescales even remotely comparable to human lifespans or human history. But we're not done yet. Not even close, because everything we've discussed so far exists within what astronomers call the local universe. We haven't even begun to talk about the truly distant cosmos. We haven't discussed the realm where the expansion of space itself becomes a major factor. We haven't addressed the ultimate horizon of the observable universe. So far, we've been discussing distances within what astronomers consider our cosmic neighborhood. We've talked about nearby stars, our galaxy, and even the closest galaxies beyond our own. But now we need to zoom out even further. We need to look at the universe on its largest scales. And this is where things become not just difficult, but fundamentally different. Because at extreme cosmic distances, we're not just dealing with vast amounts of space to cross, we're dealing with space itself expanding, carrying distant objects away from us faster than light can catch up. Let me explain what that means. The universe is expanding. This isn't controversial or speculative. It's one of the most well-established facts in all of cosmology. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because galaxies are flying through space away from some cosmic explosion site. Rather, space itself is expanding, stretching like the surface of an inflating balloon, carrying galaxies along with it. Now, here's where things get weird. When we look at galaxies that are billions of light years away, we're not just seeing them as they were billions of years ago because the light took that long to reach us. We're also seeing galaxies that are currently much farther away than they were when that light was emitted because space has been expanding during the entire journey. A galaxy that emitted light 10 billion years ago might now be 20 billion light years away due to cosmic expansion. This creates a strange situation where even traveling at light speed, you might never actually reach some distant galaxies because space is expanding faster than you can cross it. It's like running on a treadmill that's speeding up. Even running at your maximum speed, you might not make any progress if the treadmill accelerates fast enough. In cosmic terms, distant galaxies are on treadmills that are accelerating away from us, and some of them are already moving away faster than light speed relative to our position. This doesn't violate Einstein's relativity because the galaxies themselves aren't moving through space faster than light. Rather, space itself is expanding, carrying them along, and there's no speed limit on how fast space can expand. The rate of this expansion is described by something called the Hubble constant, currently measured at approximately 46 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. What this means is that for every 3.26 million light years of distance, galaxies are receding from us 46 kilometers per second faster. A galaxy 10 megaparsecs away is receding at roughly 460 kilometers per second. A galaxy 100 megaparsecs away is receding at about 4,600 kilometers per second, which is roughly 2.5% of light speed. A galaxy 1,000 megaparsecs away, that's about 3.26 billion light years, is receding at about 14% of light speed, and it keeps accelerating the farther out you go. At some distance, called the Hubble sphere, galaxies are receding from us at exactly the speed of light due to cosmic expansion. Beyond that distance, they're receding faster than light speed. Current estimates place the Hubble sphere at around 14 billion light years away, though the exact value depends on various cosmological parameters that scientists are still refining. Now here's the truly mind-bending part. Even though galaxies beyond the Hubble sphere are receding faster than light, we can still see some of them. How is that possible? Because the light they emitted in the distant past, when they were closer to us and space was expanding more slowly, has had billions of years to travel toward us. That light has been fighting against the expansion of space the entire time, getting stretched into longer wavelengths, a phenomenon called cosmological redshift, but still managing to eventually reach our telescopes. However, if you tried to travel to one of those galaxies at light speed, you'd never get there. Ever. You could travel for trillions of years at the speed of light and you'd still never reach them because space is expanding faster than you can cross it. They're beyond what's called our cosmological horizon. They're lost to us forever. Not because they're destroyed or because they've disappeared, but simply because the fabric of space-time itself is stretching too rapidly for any signal or spacecraft to ever bridge the gap. This is one of the most profound and unsettling revelations in modern cosmology. There are galaxies we can see, galaxies that exist right now in our universe, that we can never visit, never communicate with, never interact with in any way, even in principle, Even if we had infinite time and perfect technology, they're observable but unreachable. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years. Notice that this is larger than the 13.8 billion light-years you might expect, based on the universe's age. That's because of cosmic expansion. The light we see from the most distant observable galaxies was emitted when those galaxies were much closer to us. But during the 13.8 billion years it took that light to reach us, those galaxies have been carried away by expanding space to distances of 46.5 billion light-years. The total diameter of the observable universe is therefore about 93 billion light-years. That's the entire span of space from which we can receive information. Everything beyond that is, by definition, beyond our cosmic horizon. We cannot see it, we cannot detect it, and we can never reach it. But let's set aside the truly unreachable galaxies for a moment and focus on ones that are theoretically reachable, at least in principle. Let's look at some famous cosmic landmarks and discuss what it would take to visit them at light speed. The Virgo cluster is a massive collection of galaxies located about 53 million light-years away. It contains roughly 1,000 to 2,000 galaxies and has a total mass of about 1.2 trillion solar masses. It's one of the nearest galaxy clusters to us and dominates the gravitational landscape of our local universe. The Milky Way and Andromeda, along with dozens of smaller galaxies, are actually being pulled toward the Virgo cluster, though we'll never collide with it because cosmic expansion will pull us apart first. 53 million years at light speed. That's how long it would take to reach the Virgo cluster. To put that in perspective, 53 million years ago, Earth was recovering from the Cretaceous-Paleogene extinction event that wiped out the dinosaurs. Early mammals were diversifying and beginning to fill ecological niches left vacant by the vanished dinosaurs. The entire age of mammals, the entire evolutionary story from those small, shrew-like creatures to elephants, whales, primates, and humans, all of that happened in roughly the time it would take light to travel from the Virgo cluster to Earth. The Coma cluster, another massive galaxy cluster, sits about 330 million light-years away, 330 million years at light speed. When light left the Coma cluster and began its journey to Earth, vertebrates had just begun to colonize land. Fish with primitive lungs and sturdy fins were hauling themselves onto muddy shores for the first time. Plants had barely begun to grow more than a few feet tall. No trees existed, no flowers existed, no insects had yet taken to the air. The entire history of terrestrial vertebrates, from those pioneering fish to dinosaurs to birds to mammals to humans, all unfolded during the time it took light from the Coma cluster to reach us. The Hercules Corona Borealis Great Wall, one of the largest known structures in the universe, is a galactic filament spanning roughly 10 billion light-years across. Its center lies approximately 10 billion light-years away, 10 billion years at light speed. The universe itself is only 13.8 billion years old. Light from the most distant parts of this structure was emitted when the universe was less than 4 billion years old, when the first galaxies were still forming, when the cosmos looked radically different than it does today. At light speed, you'd spend more than 2/3 of the universe's entire history just reaching this structure. But let's push to the absolute limit. Let's talk about the most distant galaxies ever observed. Thanks to the James Webb Space Telescope and other cutting-edge instruments, astronomers have detected galaxies with redshifts, indicating they're more than 13 billion light-years away in terms of light travel time. These galaxies emitted their light when the universe was only a few hundred million years old, shortly after the very first stars began to shine. The current record holder, as of the latest verified observations, is a galaxy called JADES GS Z140, detected by JWST, with light that was emitted when the universe was approximately 290 million years old. That light has been traveling toward us for over 13.5 billion years. In terms of current distance, accounting for cosmic expansion, that galaxy is now more than 33 billion light-years away. 33 billion years at light speed to reach it, assuming you could somehow overcome the fact that it's receding from us due to cosmic expansion. But here's something even more sobering to consider. That galaxy, the one that emitted the light we're seeing now, doesn't look like that anymore. We're seeing it as it was more than 13 billion years ago when it was young and actively forming stars. Today, assuming it still exists and hasn't merged with other galaxies or been torn apart by cosmic violence, it would be an ancient, mature galaxy filled with old red stars. Its star-forming days would be long over. It might not even be recognizable compared to what we see in those JWST images, and we'll never know what it looks like now. The light showing us its current state won't reach Earth for more than 33 billion years, long after our sun has died, long after Earth has been consumed or sterilized, possibly long after the Milky Way has merged with Andromeda. This is the cruelty of cosmic distances. Not only can we not visit these distant galaxies, we can't even see what they look like in their present state. We're always looking at the past, and the farther we look, the deeper into history we peer. Every observation is a glimpse of something that happened long ago, a message in a bottle cast into the cosmic ocean billions of years before the first humans walked on Earth. Now let's talk about cosmic expansion in a bit more detail, because it's important to understand exactly why even light speed is inadequate for reaching the most distant parts of the universe. When physicists say the universe is expanding, they mean that the metric of space itself is increasing. Imagine you have a ruler marked in centimeters, but the centimeters themselves are slowly growing. That's essentially what's happening to space. Every cubic meter of empty space is being stretched, creating more space. This means that as you travel toward a distant galaxy, new space is being created in the gap between you and your destination. If you're traveling at light speed toward a galaxy that's 10 billion light-years away, you might expect to arrive in 10 billion years. But during those 10 billion years, space has been expanding the entire time, stretching the distance you need to cover. Depending on how far away the galaxy is and how far space is expanding at that distance, you might find that you've made no progress at all, or even that your destination is farther away than when you started, despite traveling at light speed the entire time. This isn't just a theoretical problem, this is a fundamental feature of our universe. Cosmologists have calculated something called the event horizon, which is different from the Hubble sphere. The event horizon marks the boundary between regions of space we can theoretically reach and regions we cannot, even if we left right now at light speed and traveled forever. Current estimates place our cosmological event horizon at approximately 16 billion light-years. Any galaxy currently farther than 16 billion light-years away is forever beyond our reach, even at light speed, because cosmic expansion is carrying it away from us faster than we can approach it. And here's the final devastating fact: that event horizon is shrinking. Because cosmic expansion is accelerating, driven by dark energy, fewer and fewer galaxies remain within our reachable universe as time goes on. Galaxies that are currently just within our event horizon will slip beyond it. Regions of space that we could theoretically visit if we left right now will become unreachable if we wait too long. The universe is not just vast, it's actively, continuously, irreversibly isolating us from ever larger fractions of itself. Within 1 trillion years, galaxies beyond our local group will have receded so far that they'll no longer be visible from the Milky Way. Future astronomers, if any exist, living in the merged Andromeda galaxy, will look out at a universe that appears to contain only their own galaxy, surrounded by endless darkness. They'll have no way of knowing that billions of other galaxies exist beyond their cosmic horizon. They'll have no way of discovering that the universe is expanding because they won't see distant galaxies receding. They'll likely conclude that the universe is static, eternal, and essentially empty except for their one island of stars. They'll be wrong, but they'll have no way of knowing it. All the evidence, all the distant galaxies, all the cosmic microwave background radiation, all the clues we've used to understand our universe's origin and evolution will have faded beyond detectability. We live in a privileged time, a window of cosmic history, when the universe's grand structure is still observable, when we can still see the afterglow of the Big Bang, when distant galaxies are still within view. This window is closing, and not only can we not reach those distant galaxies at light speed, but eventually we won't even be able to see them. They'll slip beyond our cosmic horizon, their light redshifted into undetectability, leaving behind an emptiness that future civilizations might never know is an illusion. By now, you're probably feeling the weight of cosmic scale pressing down on you. You're probably beginning to understand why even science fiction usually ignores the real distances involved in space travel, why Star Trek invented warp drive and Star Wars has hyperspace, why almost every space opera imagines some magical workaround for the fundamental problem we've been discussing. Because if you stick to real physics, if you limit yourself to light speed, the universe becomes not just difficult to explore, but functionally impossible to explore for any civilization with finite lifespans and limited resources. But let me make this even more personal. Let me bring this back to something tangible, something human-scaled, so you can truly appreciate what light speed really means in practical terms. Imagine humanity achieves something incredible tomorrow. Imagine we solve every technical challenge and build a spacecraft that can travel at 99% of light speed. Not quite light speed, because that's physically impossible for anything with mass, but close enough that the difference hardly matters. We've got relativistic speeds, we've got time dilation working in our favor. We're ready to become an interstellar species. You volunteer for the first mission. You're going to Proxima Centauri, our nearest stellar neighbor, at 4.24 light-years away. At 99% of light speed, the journey takes just over 4.28 years from Earth's perspective. But here's where relativity becomes important. From your perspective aboard the spacecraft, due to time dilation, the journey only takes about 8 months. Clocks run slower when you're moving at relativistic speeds, so while Earth ages 4.28 years, you only age 8 months. You arrive at Proxima Centauri, spend some time exploring, studying the planets, collecting data, and then you turn around and come home. Total mission time from Earth's perspective, about 10 years round trip, assuming you spend a year exploring. From your perspective, maybe 2.5 years, including your exploration time. You return to Earth a hero. You've visited another star system. You've walked on alien worlds. You've seen sights no human has ever witnessed. But everyone you knew is now 10 years older. Your children grew up while you were gone. Your spouse aged a decade while you aged only 2.5 years. Your friends moved on with their lives. The world changed. Technology advanced. Politics shifted. Culture evolved. You return as a time traveler from the recent past, slightly out of sync with everyone around you. Now imagine you're more ambitious. You want to visit multiple star systems, really explore our cosmic neighborhood. You plan a grand tour, Proxima Centauri, then Alpha Centauri A and B, then Barnard Star, then Wolf 359, then Sirius, then Epsilon Eridani. That's a journey covering maybe 30 light-years total, accounting for the indirect route between stars. At 99% of light speed, accounting for time dilation, you might experience this as a 5 to 7 year journey, but back on Earth, more than 30 years have passed. You return to find that your entire generation has moved into middle age. Your parents, if they were alive when you left, might now be elderly or gone. Your children are adults with careers and possibly children of their own. The cultural landscape is completely different. The music, the fashion, the politics, the technology, everything has moved on without you. You're a living fossil, a visitor from the recent past who skipped 30 years of history. And this is for visiting just a handful of nearby stars, just the closest neighbors in our immediate vicinity. Imagine attempting to explore a meaningful portion of our galaxy. Imagine trying to catalogue even 1% of the Milky Way's star systems, which would still be between 1 and 4 billion stars. Even if you could zip from star to star at 99% of light speed, spending just a week at each system, it would take you approximately 20 million to 80 million years of Earth time to visit 1% of our galaxy's stars. Your mission would span a time frame longer than humans have existed as a species. You'd leave Earth as a human and return to find, if anything is still there, that humans have either gone extinct or evolved into something unrecognizable. The civilization that sent you would be as ancient to your returnees as Australopithecus is to us. Any attempt at systematic galactic exploration, even at near light speed, is not just impractical, but meaningless. The timescales involved dwarf anything that could be considered a civilization's lifespan, and we're still talking about just our galaxy, just the Milky Way. We haven't even addressed the question of exploring beyond our galactic shores. This is the fundamental problem that no amount of engineering can solve. The universe is structured in such a way that even its maximum speed limit is inadequate for traversing cosmic distances. It's as if the cosmos is designed to keep intelligent civilizations isolated, confined to their homeworlds, or at best their local star clusters. Some scientists call this the tyranny of the rocket equation, but I think that's understating the problem. This isn't just about propulsion. It's about the fundamental architecture of space-time itself. Now, you might be wondering, are there any loopholes? Are there any ways around this cosmic speed limit that don't involve breaking the laws of physics? The answer is complicated. Theoretically, there are concepts that might allow faster-than-light travel without actually moving faster than light locally. The most famous is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The idea is ingenious. You don't move through space faster than light. Instead, you create a bubble of space-time around your ship. Space behind the ship expands and space in front of the ship contracts. You're surfing on a wave of space-time itself, and while you're not moving faster than light relative to the space immediately around you, the bubble can move faster than light relative to distant objects. It's like creating your own localized expansion of space, similar to cosmic expansion but controllable and directed. The problem? It requires exotic matter with negative mass-energy density. We've never observed such matter, and it might not exist. Even if it does exist, the energy requirements are astronomical. Early calculations suggested you'd need more energy than exists in the entire observable universe. More recent refinements have brought that down significantly, but you'd still need something equivalent to the mass energy of Jupiter, or larger. And that's assuming the physics actually works, which is far from certain. There are questions about causality, about whether such a drive would create time paradoxes, about whether the space in front of the ship would accumulate deadly radiation that would vaporize anything in its path when you decelerate. It's a beautiful mathematical concept, but it might be nothing more than an interesting quirk of Einstein's equations with no physical realization. Wormholes are another theoretical possibility. If you could somehow connect two distant points in space through a tunnel in higher dimensional space-time, you could travel between them almost instantaneously. The problem again is exotic matter. Keeping a wormhole open requires negative energy density. Then there are questions about stability. Most theoretical wormholes collapse faster than light can cross them. And even if you could stabilize one, you'd face the problem of how to create the wormhole mouth at your destination in the first place, which seems to require traveling there through normal space first. Some physicists have proposed taking advantage of quantum entanglement, the phenomenon where particles can be correlated in ways that seem to defy classical physics. But here's the harsh truth. Quantum entanglement cannot be used to transmit information faster than light. Every attempt to use it for communication or travel runs into fundamental limitations that prevent any actual faster-than-light signaling. It's one of the most misunderstood concepts in physics, frequently misrepresented in popular media. The reality is that quantum mechanics, despite its weirdness, still respects the cosmic speed limit. There's also been speculation about using cosmic strings, hypothetical, one-dimensional defects in space-time left over from the early universe, to create closed, time-like curves that might allow time travel or shortcuts through space. But cosmic strings, if they exist at all, are unimaginably violent and energetic. They'd slice through matter like a monofilament wire through butter. Trying to use one for travel would be like trying to use a chainsaw as a staircase. Even if it were theoretically possible, the practical challenges would be insurmountable. The bottom line is this: every proposed method of faster-than-light travel either requires physics we've never observed, materials we've never seen, energy sources we can barely imagine, or creates paradoxes and problems that might make them fundamentally impossible. We can't say with absolute certainty that faster-than-light travel is impossible, but we can say that it would require either a revolutionary discovery that overturns our current understanding of physics, or engineering capabilities so advanced that they might as well be magic. For now, and for the foreseeable future, we're stuck with the universe's speed limit. We're stuck with light speed being the fastest possible velocity. And as we've seen, light speed just isn't fast enough. Not for exploring the galaxy, not for reaching other galaxies, and certainly not for traversing the observable universe. This brings us to one of the most profound implications of cosmic distances, the Fermi Paradox. Named after physicist Enrico Fermi, the paradox is usually stated as, where is everybody? If the universe is so vast, if there are hundreds of billions of stars in our galaxy alone, if planets are common, if life arises readily where conditions are right, then where are all the aliens? Why haven't we detected their radio signals? Why haven't they visited us? Why isn't the galaxy teeming with civilizations? There are dozens of proposed solutions to the Fermi Paradox, but the one we've been building toward throughout this entire discussion is perhaps the simplest. They're out there, but the distances are too great. Even at light speed, even with perfect propulsion and unlimited energy, civilizations are simply too far apart to easily detect or visit each other. A civilization around Alpha Centauri would need to deliberately beam a powerful signal at Earth, and we'd need to be listening at exactly the right frequency and time, and even then, the round-trip communication delay would be 8.5 years. Any conversation would span nearly a decade per exchange. A question asked and answered would take longer than a child's journey from birth to third grade. For civilizations hundreds or thousands of light years apart, communication becomes effectively impossible. You'd send a message knowing that the civilization that receives it, if they receive it at all, might have changed beyond recognition by the time they respond. You might ask a question and receive an answer 2,000 years later from a species that has evolved, culturally and possibly biologically, into something completely different from the one you addressed. The sheer impracticality of it means that even if thousands of civilizations exist in our galaxy, they might each be isolated islands, able to detect only their immediate neighbors, if anyone, unable to form any kind of coherent galactic community. And if civilizations are separated by millions of light years across different galaxies, they might as well exist in different universes for all the interaction they can have. The light speed limit doesn't just make travel difficult, it enforces a kind of cosmic quarantine, ensuring that intelligent species are isolated by gulfs of space and time that are almost impossible to bridge. Perhaps the great filter, the hypothetical barrier that prevents civilizations from becoming galaxy-spanning empires, isn't some catastrophic technology or evolutionary dead end. Perhaps it's simply distance. Perhaps the universe's vast scale, combined with the light speed limit, is enough to ensure that civilizations remain forever isolated, forever confined to their small corners of the cosmos, forever unable to reach out and touch another intelligence among the stars. Let's shift our focus for a moment and talk about what all of this means for the future of humanity. because whether we like it or not, whether it's frustrating or humbling or terrifying, we need to grapple with the reality that light speed isn't fast enough for the kind of cosmic exploration we've imagined in our stories and dreams. So what does that mean for us as a species? What does it mean for our long-term survival, our expansion into space, our place in the universe? First, let's consider the near-term future, the next few centuries or perhaps the next millennium. Within this time frame, humanity's focus will necessarily be on our own solar system, and that's actually a good thing because our solar system is enormous, resource-rich, and full of fascinating destinations that we could reach with realistic technology. Mars is the obvious first target for colonization. It's relatively close, it has a day length similar to Earth's, it has water ice at its poles and in its soil, and it has the raw materials needed to build a self-sustaining civilization. Getting there with current chemical rockets takes about 6 to 9 months, which is long but manageable. Future propulsion systems like nuclear thermal or nuclear electric rockets could cut that travel time considerably. The asteroid belt contains more metal and minerals than humanity has extracted from Earth in all of history. There are asteroids made of nearly pure iron and nickel, some with significant amounts of platinum group metals that are rare on Earth. Mining these resources could provide the material foundation for expanding human presence throughout the solar system. The moons of Jupiter present extraordinary opportunities. Europa almost certainly has a liquid water ocean beneath its icy crust, possibly containing twice as much water as all of Earth's oceans combined. If life exists elsewhere in our solar system, Europa is one of the most likely places. Ganymede, the largest moon in the solar system, also has a subsurface ocean and might be easier to access than Europa. Callisto is less geologically active but rich in water ice and could serve as a resource depot for missions to the outer solar system. Saturn's moon. Titan is perhaps the most Earth-like world beyond Earth itself, with lakes and rivers and rain, though made of liquid methane rather than water. It has a thick atmosphere, organic chemistry happening on a planetary scale, and conditions that might allow for exotic forms of life completely different from anything on Earth. Enceladus, another Saturnian moon, is actively venting water and organic molecules from a subsurface ocean into space, essentially offering us samples of its potentially habitable interior without requiring us to drill through kilometers of ice. Even the outer reaches of our solar system hold promise. The Kuiper Belt and Oort cloud contain trillions of icy bodies, potential sources of water and volatiles for future spacefaring civilizations. Studying these pristine remnants from the solar system's formation could reveal crucial information about how planets form and how common planetary systems like ours might be. All of this is reachable with travel times measured in months, years, or at most a few decades, using realistic, near-future propulsion technology. No light-speed travel required, no exotic physics needed, just steady engineering progress and the political will to make it happen. Within our solar system, we're not limited by the fundamental structure of space-time. We're limited only by our technology, our resources, and our commitment. But eventually, assuming humanity survives and thrives in the solar system, we'll look outward to the stars. We'll want to know if life exists on the planets orbiting Proxima Centauri. We'll want to visit the potentially habitable worlds that exoplanet surveys are discovering. We'll want to become a truly interstellar species. How do we do that when light speed isn't fast enough? The answer is generation ships, also called world ships or interstellar arcs. The concept is straightforward. You build a spacecraft large enough to sustain a complete ecosystem and a viable population of humans for the decades, centuries, or even millennia required to reach another star system. The people who launched the ship aren't expecting to arrive at the destination. Their children might not arrive. Their grandchildren might not arrive. The ship becomes a traveling world, and reaching the destination is the goal of some future generation born in transit. This sounds like science fiction, but it's actually the most realistic way to achieve interstellar travel with known physics. You don't need to go fast, you don't need relativistic speeds or exotic propulsion. You just need a ship that can function as a closed or semi-closed ecosystem for as long as the journey takes. Building such a ship would be an unprecedented engineering challenge. You'd need to create an artificial environment that can sustain not just human life, but entire food webs, recycling water, air, and nutrients indefinitely. You'd need genetic diversity in your population to avoid inbreeding problems over multiple generations. You'd need to maintain technology and knowledge across centuries, ensuring that the descendants of the original crew still know how to operate and repair the ship's systems. You'd need to solve social and political problems. How do you govern a closed society of a few thousand people for generations? How do you maintain morale and purpose when the goal is centuries away? Some proposals suggest using suspended animation or cryogenic freezing to avoid the generation ship problem entirely. If you could place the crew in some form of stasis, you could cross interstellar distances without aging, waking them only when you arrive at the destination. The problem is that we currently have no technology even remotely capable of this. We can't freeze a human and revive them later. We can't induce hibernation-like states for extended periods. Every proposal for suspended animation runs into biochemical problems that we don't know how to solve. Cells are damaged by ice crystal formation. Metabolic processes can't be stopped and restarted reliably. The brain is especially vulnerable. Even if we could overcome the medical challenges, there are engineering challenges. Who maintains the ship while everyone sleeps? If you wake someone periodically to perform maintenance, you've reintroduced the time problem you were trying to solve. If you use automated systems, you're trusting that nothing will break in a way the automation can't handle over a journey lasting decades or centuries. Another approach is the seed ship concept. Instead of sending living humans, you send frozen embryos, genetic material, or even just digital information encoding human DNA, along with artificial wombs and robots capable of raising children. When the ship arrives at its destination, it begins creating humans, raising them, educating them, and establishing a colony. This reduces the life support requirements during transit and eliminates social problems among the crew because there is no crew during the journey. The ethical problems, however, are staggering. You're essentially creating orphans by design, children who will be raised by machines with no human contact during their formative years. Who decides what culture and values these children are taught? What happens if the artificial intelligence raising them malfunctions? What if the children, upon reaching adulthood, decide they don't want to be colonists and want to return to Earth, which by then might be dozens or hundreds of years of travel away? These aren't just engineering problems. They're profound moral questions about what we owe to people who don't exist yet, but whose lives we're planning in extraordinary detail. There's also the self-replicating probe approach, sometimes called the von Neumann probe, after mathematician John von Neumann, who theorized about self-replicating machines. The idea is to send small robotic probes to nearby star systems. When a probe arrives, it uses local resources to build copies of itself, which then continue onward to other star systems. Eventually, these probes could explore the entire galaxy, visiting every star system and reporting back to Earth. The problem is that even at a significant fraction of light speed, this would take millions of years to map the Milky Way. And there's the risk that the probes might evolve or malfunction during their self-replication, potentially creating a scenario where the galaxy is filled with machines that no longer serve their original purpose. Regardless of which approach we take, the fundamental constraint remains. Interstellar travel is slow. Even with the best realistic technology we can imagine, reaching even nearby stars will take decades at minimum, more likely centuries. Building interstellar civilizations, creating networks of human settlements across multiple star systems will be a project spanning thousands or tens of thousands of years. It will require patience and commitment on timescales that human civilizations have historically struggled to maintain. Empires rise and fall in centuries. Technologies become obsolete in decades. Cultural priorities shift in generations. Can humanity commit to a project that won't show results for 1,000 years? Can we maintain the institutional knowledge and political will to see it through? History suggests this might be one of our greatest challenges, but perhaps it's also one of our greatest opportunities. Perhaps the very difficulty of interstellar travel, the fact that it requires such long-term thinking and commitment, is exactly what humanity needs to mature as a species. Perhaps struggling with these challenges, planning across generations, thinking in terms of centuries and millennia rather than election cycles and quarterly earnings, is how we evolve from a collection of competing nations into a truly unified civilization with a common purpose extending beyond our individual lifespans. Let's also consider what realistic interstellar travel means for communication with Earth. If you send a colony ship to Proxima Centauri and it takes 50 years to get there, the colonists will experience a communication delay of 4.2 years each way. They can send messages to Earth, but they'll wait 4.2 years for a response. As time goes on and the colony develops its own culture, its own priorities, its own identity, what's their relationship with Earth? Are they still part of a unified human civilization, or have they become something separate? History offers some guidance here. When European colonists settled in the Americas, communication with their homelands took weeks or months by ship. Those colonies eventually developed distinct identities and, in many cases, gained independence. The colonists were still human, still shared a cultural heritage with their countries of origin, but they weren't the same. They adapted to new environments, faced new challenges, developed new perspectives. If communication delays are measured in years rather than months, won't that isolation be even more profound? A colony at a star 10 light-years away would experience a 20-year round-trip communication delay. A question asked by a child would be answered when that child is an adult. News from Earth would be ancient history by the time it arrived. How long before such a colony stops looking to Earth for guidance and starts seeing itself as independent? And what happens when Earth and its colonies disagree? What if a colony wants to pursue technologies or social structures that Earth finds dangerous or unethical? What if Earth makes demands that the colony considers unreasonable? With years-long communication delays, there's no way to have a meaningful negotiation or to enforce any kind of authority. Each colony would be effectively autonomous, connected to Earth and other human settlements only by the thinnest threads of communication, too slow for real-time interaction, too tenuous for any kind of unified governance. This means that if humanity does become an interstellar species, we won't be a unified galactic civilization. We'll be a diaspora, a collection of related but independent human cultures, each adapting to its own world, each following its own path, connected by heritage and occasional messages, but not by any meaningful political or social unity. Over thousands of years, separated by light years of space and generations of divergent evolution, will these distant human colonies even consider each other part of the same species? Will cultural and eventually biological evolution create humans so different from one another that we might as well be different species? It's possible, in fact it's likely, if the timescales are long enough. Now let's address something that might seem counterintuitive given everything we've discussed. Despite light speed being woefully inadequate for crossing cosmic distances, it's still the fastest thing in the universe. It's still the fundamental speed limit built into the fabric of reality. And understanding why this speed limit exists, understanding what light speed actually represents in the structure of space-time, might help us come to terms with the universe we inhabit. Light speed isn't just some arbitrary number that physicists measured. It's not like the speed of sound, which varies depending on what medium sound is traveling through. Light speed in a vacuum is a fundamental constant of nature, woven into the basic equations that describe how space, time, energy, and matter relate to each other. In Einstein's special relativity, light speed is more accurately understood as the speed of causality. It's the maximum rate at which cause and effect can propagate through the universe. It's the speed at which information can travel. When you think about it this way, light speed isn't really about light at all. It's about the structure of space-time itself. Here's another way to think about it. In our everyday experience, we think of space and time as separate things. You can move through space while time passes. You can sit still in space while time continues flowing. But Einstein showed us that space and time are actually woven together into a single, four-dimensional fabric called space-time. Every object in the universe is always moving through space-time at exactly the speed of light. Always. You're doing it right now. Wait, you're probably thinking, I'm sitting still. How am I moving at the speed of light? The answer is that you're moving through time. When you're stationary in space, all of your motion through space-time is in the time direction. You're traveling forward through time at 1 second per second, which is equivalent to moving through space-time at light speed. When you start moving through space, some of your space-time motion that was previously in the time direction gets redirected into spatial directions. You're still moving through space-time at light speed, but now some of that motion is through space and correspondingly less is through time. This is time dilation. The faster you move through space, the slower you move through time from the perspective of someone who isn't moving with you. Light itself, photons, move through space at the maximum possible rate, which means they don't move through time at all. From a photon's perspective, if photons could have perspectives, no time passes during their journey. A photon emitted from a distant galaxy billions of years ago and absorbed by your eye right now experiences zero elapsed time between emission and absorption. Its entire journey from our perspective, spanning eons, is instantaneous from its own frame of reference. This is why nothing with mass can reach light speed. To do so would mean moving entirely through space with no motion through time, which would require that object to have no duration, no before and after, no causal relationship between its emission and its absorption. It would have to be timeless, and anything with mass inherently exists in time. It has a history. It has internal processes that require time to unfold. So the light speed barrier isn't some arbitrary cosmic law that a sufficiently advanced civilization might circumvent. It's a fundamental feature of how reality is structured. Breaking it wouldn't just be difficult. It would be logically contradictory, like asking what's north of the North Pole or what happened before time began. The question itself might not make sense, but understanding this doesn't make the vastness of space any less frustrating. It doesn't change the fact that the universe is structured in a way that makes exploration extraordinarily difficult. Why is the universe like this? Why is space so vast? Why is the speed of causality so limiting? These are profound questions that touch on cosmology, philosophy, and perhaps even the anthropic principle, the idea that the universe must have properties compatible with the existence of observers, because if it didn't, we wouldn't be here to observe it. Some physicists have argued that if the speed of light was significantly faster, the universe might not be stable. Chemical reactions might happen differently. Atoms might not form as they do. The delicate balance of forces that allows matter to exist in stable configurations might be disrupted. In other words, the speed of light might be exactly what it is, because if it were any different, we wouldn't exist to complain about it. Similarly, the vast distances between stars might be a necessary consequence of how galaxies form and stars are distributed. If stars were packed more densely, stellar interactions and collisions would be more common, potentially disrupting planetary systems before life could evolve. The radiation environment would be more hostile. Supernovae would threaten nearby stars more frequently. It's possible that the galaxy we observe, with its vast emptiness and isolated stars, is precisely the kind of galaxy that can host long-lived, stable planetary systems where complex life has time to evolve. From this perspective, the frustrating emptiness of space, the impossibly vast distances, the light speed barrier that makes travel so difficult, all of these might be necessary preconditions for our existence. We're not struggling against arbitrary cosmic constraints. We're facing the consequences of living in a universe structured in the only way that allows us to be here at all. That's simultaneously comforting and unsettling. It suggests we're not being unfairly limited by a cruel universe, but it also suggests that these limitations might be absolutely fundamental, with no clever workarounds waiting to be discovered. Now let's talk about what we can actually observe and learn from the universe despite not being able to travel through it. Because even though we can't visit distant galaxies, we can still study them. Even though we can't reach most of the cosmos, we can still learn from the light that reaches us. And in some ways, that light carries richer information than any probe we could send. Every photon that enters a telescope carries information about where it came from. Its wavelength tells us about the chemical composition of the object that emitted it, because different elements absorb and emit light at characteristic wavelengths, creating spectral fingerprints. The photon's redshift tells us how fast the source is moving away from us due to cosmic expansion, which tells us how far away it is and how the universe has expanded since the photon was emitted. Its polarization can tell us about magnetic fields in the source. Its intensity tells us about the source's brightness, and comparing that to its apparent brightness tells us its distance. Multiple photons arriving at slightly different times can tell us about the size of the emitting region. Subtle variations in brightness can reveal orbiting planets or binary companion stars. From light alone, astronomers have mapped the structure of galaxies billions of light years away. We've determined the temperature, composition, and age of stars we'll never visit. We've discovered thousands of exoplanets around distant stars and characterized their atmospheres. We've detected the merger of black holes over 1 billion light-years away through gravitational waves, ripples in space-time itself, traveling at light speed. We've imaged the cosmic microwave background, the faint afterglow of the Big Bang, and used it to measure the universe's age, composition, and geometry with stunning precision. The James Webb Space Telescope, launched in December 2021, is observing galaxies that existed when the universe was less than 5% of its current age. It's seeing the first galaxies that formed after the cosmic dark ages, when the universe had cooled enough for atoms to form but before stars had ignited. These galaxies are more than 13 billion light-years away in light travel time, more than 30 billion light-years in actual distance, accounting for expansion. We'll never visit them. We'll never send a probe there, but we can study them in exquisite detail, learning how galaxies form, how stars begin, how the heavy elements necessary for planets and life are created and distributed. In a very real sense, astronomy is a form of time travel. When we look at distant objects, we're not seeing them as they are now. We're seeing them as they were when the light left them. The farther we look, the further back in time we see. The most distant objects observable are showing us the universe as it existed over 13 billion years ago, when it was young and hot and profoundly different from today. We can watch cosmic history unfold just by looking at objects at different distances. Nearby galaxies show us the modern universe. Intermediate distance galaxies show us the universe billions of years ago. The most distant galaxies show us the universe in its infancy. By combining observations across this vast span of distances and times, astronomers have reconstructed the universe's history from the Big Bang to the present. We know that the universe began in an incredibly hot, dense state, approximately 13.8 billion years ago. We know it expanded and cooled, allowing particles to form, then atoms, then the first stars. We know those stars lived and died, creating heavy elements that were scattered into space, enriching the next generation of stars. We know galaxies formed and evolved, colliding and merging, creating the cosmic web of structure we see today. We know that dark matter, some mysterious substance that doesn't emit light but exerts gravitational influence, outweighs normal matter by about 5 to 1. We know that dark energy, an even more mysterious component, is causing the universe's expansion to accelerate, driving galaxies apart at ever-increasing rates. All of this knowledge comes from light, from photons that traveled across cosmic distances to reach our instruments. We didn't need to go there. The information came to us. This is the consolation prize for living in a universe too vast to explore directly. We can still study it, we can still learn from it. We can still participate in the grand project of understanding existence, even if we can't physically traverse it. But there's a melancholy aspect to this as well. We're observers, not participants, in most of the cosmic story. We can watch distant galaxies collide, but we can't visit them. We can detect planets around other stars, but we can't walk on their surfaces. We can study the life cycles of stars, but we can't travel to them before they die. We're like someone confined to a single room with windows looking out on an enormous, fascinating world. We can see it, we can learn about it, we can appreciate its beauty and complexity, but we can't step outside, we can't touch it, we can't interact with it in any meaningful way. Is it enough to be observers? Is knowledge without experience, understanding without interaction, satisfying? For some people, absolutely. The joy of discovery, the thrill of understanding the beauty of the cosmos revealed through careful observation and analysis. These are profound rewards. Astronomers spend their entire careers studying objects they'll never visit, and most find it deeply fulfilling. But there's also something in the human spirit that wants to explore, to venture into unknown territory, to plant a flag or leave a footprint, or simply stand in a place no one has stood before. And for that urge, for that deep-seated need to explore and expand and reach beyond our current boundaries, the universe's vastness is a cruel limitation. Let's consider for a moment what it would actually take to build a realistic interstellar vessel using technology that doesn't violate known physics. Because even though we've established that light speed isn't fast enough, and even though reaching significant fractions of light speed is extraordinarily difficult, it's still worth understanding what's theoretically possible versus what's actually achievable. If we want to reach even 10% of light speed, which would get us to Proxima Centauri in about 42 years, we face staggering engineering challenges. The most straightforward approach is the fusion rocket. Nuclear fusion, the process that powers stars, releases enormous amounts of energy by combining light atomic nuclei into heavier ones. If we could build a rocket that uses fusion reactions for propulsion, expelling the fusion products as exhaust, we could theoretically achieve velocities of several percent of light speed. The problem is that we haven't yet achieved controlled fusion that produces more energy than it consumes here on Earth, let alone miniaturized it into a spacecraft engine. Even if we solve the fusion problem, there's the issue of fuel. Hydrogen fusion requires extremely high temperatures and pressures difficult to maintain in a rocket engine. The most efficient fusion reaction for propulsion would probably be deuterium and helium-3, but helium-3 is incredibly rare on Earth. You'd need to mine it from the Moon or from the atmospheres of gas giant planets, adding yet another layer of difficulty to an already challenging project. Then there's the rocket equation itself, the fundamental relationship between a rocket's mass, its fuel mass, and its final velocity. To achieve high speeds, you need exponentially larger amounts of fuel. To reach 10% of light speed with a fusion rocket, you might need a ship, where 99% or more of the initial mass is fuel. The actual payload, the part carrying crew or cargo or scientific instruments, becomes a tiny fraction of the total launch mass. This creates a cascade of problems. More mass means more structure to hold it together, which means more mass, which means more fuel, which means more structure, and so on. Engineers call this the tyranny of the rocket equation, and it severely limits what's achievable with conventional propulsion. One proposed solution is the Bussard ramjet, a concept proposed by physicist Robert Bussard in 1960. The idea is brilliant. Don't carry your fuel with you. Instead, use a giant magnetic scoop to collect hydrogen from the interstellar medium, fuse it as you go, and use the fusion products for propulsion. The interstellar medium is thin, only about 1 atom per cubic centimeter on average, but if your scoop is large enough, thousands of kilometers across, you could collect enough fuel to sustain fusion. You'd start with a conventional rocket to get up to speed, but once you're moving fast enough, the ramjet takes over, potentially allowing you to accelerate continuously to relativistic velocities. The problems, however, are numerous. The magnetic scoop would need to be enormous and would require tremendous amounts of energy to maintain. The incoming hydrogen would be hitting your scoop at a significant fraction of light speed, making it incredibly energetic and difficult to funnel into your fusion reactor. Some calculations suggest that the drag created by the magnetic field interacting with the interstellar medium might be greater than the thrust produced, meaning the ramjet would actually slow you down rather than speed you up. And the interstellar medium isn't uniformly distributed. In some regions it's denser, in others it's more sparse. Navigating through varying fuel densities while maintaining stable fusion would be extraordinarily difficult. Another approach is the nuclear pulse propulsion concept, exemplified by Project Orion, a design study conducted in the 1950s and 60s. The idea is audaciously simple. Throw nuclear bombs out the back of your spacecraft, detonate them, and ride the shockwave. Each explosion gives you a kick of acceleration. String together enough explosions and you could reach several percent of light speed. Project Orion was actually taken quite seriously for a while, with detailed engineering studies showing it was technically feasible with 1960s technology. The spacecraft would have a pusher plate made of a special ablative material that could withstand repeated nuclear blasts, with shock absorbers connecting it to the crew section. The problems are political and practical rather than purely technical. Detonating thousands of nuclear devices, even in space, raises obvious concerns about nuclear proliferation and environmental contamination. The Partial Nuclear Test Ban Treaty of 1963 effectively killed Project Orion by prohibiting nuclear explosions in space. And even if we revived the concept, the engineering challenges would be formidable. You'd need to manufacture thousands of precisely calibrated nuclear charges, each optimized for propulsion rather than destruction. You'd need a pusher plate that could survive repeated nuclear blasts without degrading. You'd need a system to eject the charges at precisely the right timing and position, and you'd need to protect the crew and electronics from radiation, electromagnetic pulses, and the sheer violence of the repeated explosions. The most viable near-term option for interstellar travel might be the laser sail or light sail concept. Instead of carrying fuel, your spacecraft is essentially a giant mirror attached to a minimal payload. A powerful laser array, probably positioned in space near Earth or the Sun, beams energy to your sail, accelerating it with photon pressure. Because you're not carrying fuel, you avoid the rocket equation problem. The acceleration continues as long as the laser can maintain focus on your sail, potentially pushing you to 10 or 20% of light speed. The Breakthrough Starshot initiative, funded by Russian billionaire Yuri Milner and backed by physicists like Stephen Hawking before his death, is exploring exactly this concept. The plan is to build an array of ground-based lasers that can collectively produce gigawatts of power and focus it on tiny spacecraft, each about the size of a postage stamp with a sail a few meters across, weighing just a few grams. These ultralight probes would be accelerated to 20% of light speed, reaching Proxima Centauri in about 20 years. Once there, they'd take pictures, collect data, and transmit it back to Earth, where it would arrive 4.2 years later. The challenges are substantial but not physics-defying. You need incredibly precise laser focusing to keep the beam on a sail that's rapidly accelerating away and will soon be millions of kilometers distant. You need sails that can reflect laser light without absorbing enough heat to vaporize. You need spacecraft electronics that can survive the acceleration, the cosmic radiation during the journey, and still function when they arrive. You need miniaturized cameras, sensors, and transmitters capable of sending data across light years. And you need all of this to work with no possibility of repair or adjustment once the probe leaves Earth. But it's possible. Every required component has a path to development with known physics and plausible engineering. Breakthrough Starshot might actually launch interstellar probes within a few decades. They won't carry humans, they won't be able to land on planets. they'll essentially be flybys happening at 20% of light speed, giving them only hours to observe the Proxima Centauri system before racing past. But they'd prove that interstellar travel is possible, that we can reach other stars within a human lifetime, that the data we collect about exoplanets isn't limited to observations from Earth. The problem with scaling this up to crewed missions is obvious. A postage stamp-sized probe is one thing, a spacecraft large enough to support human life, with all the necessary life support, radiation shielding, food production, waste recycling, medical facilities, and living space for a crew, would mass many tons. Accelerating that much mass to 20% of light speed with a laser sail would require far more powerful lasers, far larger sails, and far more energy than the breakthrough Starshot proposal envisions. And there's another problem. You can't use a laser from Earth to slow down when you reach your destination. The spacecraft would zip through the target system at 20% of light speed, with no way to stop. You could carry a second sail facing forward and use the light from the destination star to brake. But stars produce much less concentrated light than a laser array, making deceleration slow and inefficient. Or you could plan a flyby mission only, accepting that you'll race through the system in a matter of hours or days, collecting what data you can before continuing into the darkness beyond. For colonization, for actually settling another star system, you'd need either a different propulsion method or a willingness to take centuries or millennia for the journey, settling for much lower velocities where deceleration is more manageable. This brings us back to generation ships, those immense vessels designed to sustain human life for the duration of a multi-century journey. The engineering challenges are different from high-speed propulsion, but no less daunting. You need a closed-loop life support system that can recycle air, water, and nutrients for generations without significant loss or contamination. Earth's biosphere has been perfecting this for billions of years, and it works because it's planetary in scale, with enormous buffers and reserves. A generation ship would be trying to replicate this in a tiny, isolated system with no room for error. Any imbalance, any gradual accumulation of toxins, any failure of a key species in your artificial ecosystem, and the entire mission could fail. You need genetic diversity in your crew. Too small a population and you risk inbreeding depression, the accumulation of harmful genetic traits that reduce fitness and fertility. Estimates vary, but most geneticists suggest a minimum founding population of several hundred individuals to maintain genetic health over many generations, and thousands would be safer. That means your ship needs to support thousands of people with all their needs for food, water, space, and medical care for the entire journey. You need to maintain social cohesion across generations. The people who arrive at the destination will be descendants of the original crew, many generations removed. They'll have been born on the ship, lived their entire lives on the ship, and the destination will be an abstract concept they've only heard about in stories. How do you motivate them to complete a mission that their great-great-great-grandparents started? How do you prevent social breakdown, mutiny, or a decision by one generation to simply give up on the destination and continue drifting through space indefinitely? Science fiction has explored these themes extensively. Stories like Arthur C. Clarke's Rendezvous with Rama or Kim Stanley Robinson's Aurora grapple with the psychological and sociological challenges of generation ships. And the conclusion many of these stories reach is sobering. It might not work. The challenges might be insurmountable not because of engineering, but because of human nature. There's another approach we haven't fully explored yet, one that's perhaps more philosophical than technological, but worth considering nonetheless. If we can't physically travel to distant stars and galaxies in any reasonable time frame, perhaps we should reconsider what it means to explore. Perhaps physical presence isn't the only form of exploration that matters. Perhaps sending our knowledge, our culture, our essence in some form that doesn't require transporting biological bodies across light years is a valid alternative. This is the concept behind messages like the Voyager Golden Records, the plaques on Pioneer 10 and 11, and various radio messages beamed toward nearby stars. These aren't attempts at travel, but a communication at saying we exist, we're here, this is who we are, to any intelligence that might be listening. The Voyager Golden Records are particularly poignant. They contain sounds and images selected to portray the diversity of life and culture on Earth, launched aboard both Voyager spacecraft in 1977. They include greetings in 55 languages, music from different cultures and eras, sounds from nature and human activity, and 116 images showing mathematical and physical definitions, human anatomy, landscapes, and scenes of daily life. Carl Sagan, who chaired the committee that assembled the records, described them as a message in a bottle cast into the cosmic ocean. The chances of them being found are infinitesimally small. Space is vast, the Voyager probes are tiny, and they're not headed toward any particular star. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445, which is reasonably close by cosmic standards, but still far enough that the probe would be invisible and undetectable unless someone was specifically looking for it. But the gesture matters. The act of creating these records, of carefully selecting what to include, of thinking about how to communicate with an alien intelligence, forced us to confront questions about who we are, what defines humanity, what we want to say about ourselves to the universe. In that sense, the Golden Records have already succeeded. They've made us think deeply about our place in the cosmos. Perhaps the future of interstellar exploration isn't about sending humans, but about sending information. Digital messages containing everything we know, everything we've learned, everything we've created, transmitted toward promising star systems. If those messages are ever received by another intelligence, they could reconstruct our science, our history, our culture. In a sense, humanity would have reached those stars, not physically, but informationally. Some futurists have proposed even more speculative concepts. If we develop sufficiently advanced artificial intelligence, we could send AI probes to other star systems. Upon arrival, these probes could use local resources to build infrastructure, study the star system, and potentially even create biological organisms from digital genetic information. They could, in theory, recreate humans or other Earth life forms using raw materials found at the destination. This concept, sometimes called directed panspermia or seeding missions, would allow humanity to spread across the galaxy without the need for generation ships or faster-than-light travel. The timeline would still be measured in thousands or millions of years, but it's at least theoretically possible with extensions of current technology. The philosophical questions, however, are profound. If an AI creates humans from genetic information at a distant star, are those humans really us? Are they a continuation of humanity or something new? Do they have rights? Do we have obligations toward them? Who decides what knowledge and culture to encode in the AI's programming? These aren't just thought experiments. If we're serious about becoming a multi-star species, we'll need to answer these questions eventually. There's also the possibility of what some call cosmic archaeology. If other civilizations have existed in our galaxy, and if they were more successful at interstellar travel than we've been, they might have left traces. Not necessarily alien visitors to Earth, which despite countless claims has no credible evidence, but artifacts in space. Probes orbiting distant stars, structures on asteroids or moons, perhaps even signs of megastructures like Dyson spheres, hypothetical constructs that would surround a star to capture all of its energy. Searching for these traces for evidence of other civilizations past or present is a form of exploration that doesn't require us to travel. We can search using telescopes, studying anomalies in star systems, looking for patterns that suggest artificial origin. The search for extraterrestrial intelligence, or SETI, has been doing this for decades, listening for radio signals that might indicate technological civilizations. So far, we've found nothing conclusive, but we've only searched a tiny fraction of the sky at a limited range of frequencies. It's like dipping a cup into the ocean and finding no fish in that cup, concluding that the ocean is empty. The absence of evidence isn't evidence of absence, especially when the search space is so enormous. But the ongoing silence, the fact that we haven't detected obvious signs of alien civilizations despite decades of searching, is itself information. It suggests several possibilities, all of them fascinating and somewhat troubling. Perhaps life is much rarer than we hoped. Perhaps the conditions necessary for life to arise are so specific, so unlikely, that Earth is genuinely unusual and civilizations are separated by such vast distances that contact is essentially impossible. Perhaps life is common, but intelligent life is rare. Maybe most biospheres are filled with bacteria and simple organisms, and the jump to complex multicellular life, to nervous systems, to intelligence is improbably difficult. Perhaps intelligence is common, but technological civilization is rare. Maybe most intelligent species don't develop technology, or they do, but then destroy themselves before they become spacefaring. This is the great filter hypothesis, the idea that there's some step in the progression from non-life to galaxy-spanning civilization that's extremely unlikely. The terrifying question is whether that filter is behind us or ahead of us. If it's behind us, if the hard step was the origin of life or the evolution of intelligence, then we're past the filter, and the future is potentially bright. If it's ahead of us, if civilizations typically destroy themselves through nuclear war, environmental collapse, artificial intelligence gone wrong, or some other catastrophe we haven't imagined yet, then our future is precarious. The cosmic silence might be telling us something important about the universe and our place in it. It might be warning us that technological civilizations are short-lived, that the same capabilities that allow a species to leave its planet also enable it to destroy itself, and very few civilizations navigate that transition successfully. Or perhaps civilizations are out there, but they're quiet. Maybe once you achieve a certain level of technology, broadcasting your presence becomes unnecessary or unwise. Maybe advanced civilizations communicate in ways we haven't imagined, using methods or frequencies we're not monitoring. Maybe they've detected us but chosen not to respond, either because we're too primitive to be interesting or because they have policies against interfering with developing civilizations. This is the zoo hypothesis, the idea that Earth is being observed but not contacted, like animals in a nature preserve. It's unfalsifiable and somewhat anthropocentric, but it can't be completely ruled out. Or perhaps the most unsettling possibility, maybe we're simply first. Maybe in our region of the galaxy, in this period of cosmic history, we're the first civilization to arise. Someone has to be first, after all. If it's us, we carry a profound responsibility. How we develop, what we do with our technology, whether we survive or destroy ourselves, might set the template for all civilizations that follow. Let me bring this back to something more immediate and personal. What does all of this mean for you, for me, for humans, living right now in the 21st century? We've established that the universe is almost unimaginably vast, that light speed isn't fast enough to explore it, that we're confined by the laws of physics to our small corner of the cosmos, at least for the foreseeable future. How should we respond to this knowledge? One response is despair or resignation. If we can't reach the stars, if the universe is too big and we're too small, why bother? Why invest in space exploration at all? Why not focus exclusively on problems here on Earth and accept that humans are a planetary species confined to this one world for our entire existence? I understand the appeal of this perspective, especially when Earth faces so many pressing challenges that demand attention and resources. Climate change, poverty, disease, conflict, these are immediate problems requiring immediate solutions. Spending billions on space telescopes or Mars rovers can seem frivolous when people are suffering here and now, but I'd argue that this is a false dichotomy. The same technological development, scientific understanding, and long-term thinking required for space exploration benefits us here on Earth. Satellite technology improves communication, navigation, weather forecasting, and climate monitoring. Materials science developed for spacecraft leads to better solar panels, more efficient batteries, and stronger lightweight materials with countless terrestrial applications. The challenges of creating closed-loop life support for spacecraft directly inform efforts to create sustainable systems here on Earth. Learning to recycle water and air, to grow food efficiently in confined spaces, to minimize waste and maximize resource utilization, these skills are relevant whether you're on a spaceship or a planet with limited resources. Moreover, the perspective gained from space exploration, the overview effect reported by astronauts who see Earth from space, fundamentally changes how we view ourselves and our planet. Seeing Earth as a small, fragile blue sphere floating in the vastness of space with no visible borders or divisions, just a single interconnected ecosystem, profoundly affects people's understanding of our shared humanity and our collective responsibility for our world. Carl Sagan captured this beautifully in his reflection on the pale blue dot photograph taken by Voyager 1 from beyond Neptune, showing Earth as a tiny pixel in a beam of sunlight. He wrote, "That's here, that's home, that's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." This perspective, this cosmic humility, is valuable. It reminds us that our tribal conflicts, our ideological disputes, our national rivalries are all playing out on an infinitesimally small stage. It doesn't make those conflicts unimportant, but it provides context. It reminds us that we're all in this together, all inhabitants of the same tiny world, all dependent on the same thin layer of atmosphere and the same delicate balance of conditions that make life possible. Space exploration also serves another crucial function. It inspires. It captures imaginations, encourages young people to pursue science and engineering, and reminds us that humanity is capable of extraordinary achievements when we work together toward ambitious goals. The Apollo program, which landed humans on the Moon between 1969 and 1972, inspired an entire generation of scientists, engineers, and explorers. The images of Earth rising over the lunar horizon, of human footprints in lunar dust, of our species leaving our homeworld for the first time, these weren't just scientific achievements, they were cultural moments that expanded our collective sense of what's possible. We need that inspiration now, perhaps more than ever. In an era of cynicism and division, when so much news is discouraging and so many problems seem intractable, space exploration offers hope. It shows us that humans can accomplish incredible things. It demonstrates that science and technology, properly applied, can answer questions and overcome challenges that once seemed impossible. When the James Webb Space Telescope delivered its first images in July 2022, showing the universe in unprecedented detail, the public response was overwhelming. People around the world were captivated by these images of distant galaxies, stellar nurseries, and exoplanet atmospheres. For a moment, humanity united in wonder at the cosmos. That sense of wonder is valuable in itself. It's part of what makes us human. Since our ancestors first looked up at the night sky and wondered what those lights were, humans have been driven by curiosity about the universe. That curiosity led to agriculture, to civilization, to mathematics and science, to everything we consider progress. Abandoning space exploration would be abandoning part of our nature, the part that asks questions and seeks answers, the part that looks beyond the immediate and imagines possibilities. But let's be honest about the limitations. We've spent this entire discussion establishing that light speed isn't fast enough, that the universe's vastness makes exploration extraordinarily difficult, that we're confined by physics to timescales and distances that challenge everything we consider reasonable. How do we maintain hope and inspiration in the face of such daunting constraints? I think the answer lies in adjusting our expectations and our timescales. Humanity has existed as a species for roughly 300,000 years. Civilization has existed for perhaps 10,000 years, industrial civilization for about 250 years, space exploration for about 65 years. We're incredibly young as a spacefaring species. We've barely started. The challenges we face, the limitations we're confronting, these aren't signs of failure. They're signs that we're attempting something genuinely difficult, something at the edge of what's possible. Perhaps we need to think not in terms of individual human lifetimes, but in terms of civilizational timescales. If it takes 10,000 years to establish human presence throughout our solar system, that's still a blink of an eye in cosmic time. If it takes 100,000 years to send colony ships to nearby stars and establish settlements, that's still just a fraction of how long humans have existed. If it takes millions of years to spread throughout the galaxy, assuming we find ways to maintain continuity across such spans, that's still less time than many species have existed on Earth. We're used to thinking in terms of years or decades because those are the timescales of human life. But civilizations, if they survive, operate on much longer timescales. The pyramids of Egypt have stood for nearly 5,000 years. The Great Wall of China has existed in various forms for over 2,000 years. These structures were built by civilizations thinking beyond individual lifetimes, planning for futures their builders would never see. Maybe interstellar expansion requires a similar mindset. Maybe we need to accept that the humans who launch a colony ship to another star won't be the ones who arrive. Maybe we need to think of humanity not as individuals, but as a continuous chain across generations, a species-level project that extends far beyond any of us personally. This requires a kind of faith, not religious faith necessarily, but faith that the project is worthwhile even if we won't see its completion. It requires belief that future generations will value what we start, that they'll continue the work, that the long-term flourishing of humanity is worth pursuing even when the timescales involved exceed our ability to comprehend them personally. Some people find this motivating. They're inspired by being part of something larger than themselves, by contributing to a story that extends far into the future. They find meaning in the idea that their work, their contributions, will matter to descendants thousands of years hence. Others find it alienating. If the payoff is so distant that no one alive today will benefit, why bother? Why sacrifice resources and effort for a future so remote it's essentially hypothetical? There's no single answer to this. It's a question of values, of what you find meaningful, of how you conceptualize your relationship to the future. But I'd suggest that we're already constantly making decisions that affect the distant future. When we address climate change, or preserve ecosystems, or invest in education, we're acting for the benefit of people who don't exist yet. We're acknowledging that we have some responsibility to the future, even if that future extends beyond our personal experience. Interstellar exploration is an extension of that same principle, just on a longer timescale and a larger spatial scale. It's saying that humanity's story shouldn't end with our generation or our planet, that we have some responsibility to give our descendants the opportunity to continue to explore, to ask questions, to be part of the cosmic story. Now let's address something we've been dancing around throughout this entire discussion, the possibility that we're wrong. The possibility that our current understanding of physics is incomplete, that there are loopholes or workarounds we haven't discovered yet, that faster-than-light travel might be possible through mechanisms we don't currently understand. Science has been wrong before. Newtonian physics seemed complete and correct until Einstein showed that it was an approximation that breaks down at high speeds and strong gravitational fields. Quantum mechanics revealed a microscopic world that operates on principles wildly different from our everyday experience. Who's to say that our current understanding is final? Maybe there's some deeper theory, some extension of relativity or quantum mechanics that allows for faster-than-light travel or shortcuts through space-time. Maybe we'll discover new physics that makes the impossible possible. It's worth staying open to this possibility. Science progresses by challenging assumptions and testing boundaries. The greatest discoveries often come when someone questions something everyone else took for granted. So we should absolutely continue researching, exploring the edges of our knowledge, looking for gaps or contradictions in our theories that might point toward new understanding. But, and this is crucial, we can't count on it. We can't base our plans and our civilization's future on the hope that magical new physics will save us from the limitations we currently face. That would be like someone in the 1500s deciding not to build ships because maybe in the future someone will invent teleportation. Maybe they will, but in the meantime, you still need ships. We need to work with the physics we know, the technology we can plausibly develop, and the constraints we can measure. If someday we discover a way around the light speed barrier, fantastic. That will revolutionize everything and open possibilities we can barely imagine. But until that day comes, if it ever does, we need to grapple with the universe as we understand it. And that universe is one where light speed is the limit, where distances are vast, where exploration is difficult, and where patience and persistence on civilizational timescales are required for any hope of reaching the stars. There's something beautiful in that struggle, something ennobling in accepting the challenge despite its difficulty. Humans have always pushed boundaries. We've crossed oceans, climbed mountains, ventured into deserts and jungles and polar ice. We've done these things not because they were easy, but because they were hard, because they challenged us, because they expanded our horizons and our understanding of what's possible. Space is the ultimate frontier, the hardest challenge we've ever faced. The fact that it's difficult doesn't make it less worthwhile. If anything, it makes it more worthwhile. Easy victories don't inspire. They don't push us to grow and develop and become more than we were. Difficult challenges that require centuries or millennia of effort, challenges that demand the best of our intelligence and creativity and cooperation. Those are the challenges that define civilizations. Perhaps struggling with the vastness of space, learning to accept and work within the constraints of light speed, developing the patience and long-term thinking required for interstellar expansion, perhaps this is exactly what humanity needs. Maybe the journey matters more than the destination. Maybe learning to think across generations, to plan for futures we won't personally witness, to value knowledge and exploration for their own sake rather than for immediate practical benefit. Maybe this is how we mature as a species. Carl Sagan once said that we live in a society exquisitely dependent on science and technology, in which hardly anyone knows anything about science and technology. He worried that this ignorance would lead to disaster, that we'd make terrible decisions because we didn't understand the tools we were using or the consequences of our actions. Space exploration, astronomy, cosmology, these fields address that ignorance. They teach us where we came from, how the universe works, what's possible and what isn't. They provide context for our existence, perspective on our place in the cosmos. That education, that understanding is valuable whether or not we ever leave our solar system. Even if humanity never becomes an interstellar species, even if we remain forever confined to our one-star system, the knowledge we gain from studying the universe makes us wiser, more humble, more capable of navigating the challenges we face. And if we do eventually spread to the stars, if our descendants thousands of years from now walk on worlds orbiting distant suns, it will be because we started now, because we invested in the science and technology, because we maintained the commitment across generations, because we decided that despite the difficulty, despite the timescales involved, the effort was worthwhile. Every journey begins with a single step. For interstellar travel, we're still taking those first stumbling steps. We've sent probes to the edge of our solar system. We've detected thousands of exoplanets around other stars. We're beginning to characterize their atmospheres and search for signs of life. We're developing propulsion concepts that might eventually achieve significant fractions of light speed. We're learning to think beyond our planet, beyond our immediate circumstances, toward a longer and larger future. The universe is vast. Light speed isn't fast enough. But we're here, we're curious, and we're not giving up. And that, in the end, might be the most important thing of all. If this journey through cosmic distances and the limitations of light speed has fascinated you, if you want to explore these concepts even further with stunning visuals and a deeper dive into exactly how far humanity could theoretically travel, I invite you to watch my video called The Absolute Limit of Human Travel Through Space. In it, we'll explore the ultimate boundaries of where we can go, what we can reach, and what forever remains beyond our grasp. We'll visualize these impossible scales in ways that make them more tangible and confront the humbling reality of our cosmic neighborhood.